So we're going to be defining two types of energy today, dealing with applications that we're going to use quite frequently. One is gravitational potential energy, one is kinetic energy. These are things that are really kind of a review from Science 10. But as I said to you before, we're going to expect you to understand things at a deeper level and apply them to more complicated situations. Once we have talked about the different forms of energy, we're going to be solving some problems with them. So, energy is the ability to do work, and work is a transfer of energy. This is from yesterday. Today we're looking at different types of energy. If work is a transfer of energy, then we need to be able to identify frequently what type of energy is being transferred. Is it kinetic? Is it potential? Is it some other type of energy? And in general, there are 4 classifications of energy. And this is just my classification. I'm sure you could break it down to different classifications, but I like this grouping for high school physics. The first one is kinetic energy. Kinetic energy is energy that an object has due to its motion. All right? Why does an object in motion have energy? Because it has the ability to do work. If you agree that me taking this trash can and doing this to it is doing work, and you do, don't you? Then can't I accomplish the same thing by throwing an object at it? I'm not going to, but if I took a physics textbook and I hurled it at that waste paper basket, I would be giving the textbook kinetic energy. And it has that energy as it's moving through the air, and then when it hits that waste paper basket, it does work to it, demonstrating that objects in motion have energy. The example I'm saying is if you've ever been hit in the head by a baseball, you know that a moving baseball has energy because it does work to your head. Whenever you get an object to get kinetic energy, it's because it has been accelerated. This is a really important idea. And what I'm telling you is you have to associate the net force with kinetic energy. If the net force is 0, then there will be no transfer of kinetic energy. It's the net force that causes the object to speed up, giving it kinetic energy. Because net force results in acceleration. The work done in this case is the gain in kinetic energy. And I'm just putting this condition here, assuming there are not other forms of energy present. So, if I apply a net force to an object on a horizontal surface, I will give it kinetic energy. If I apply a net force to an object along a ramp, it's going to gain kinetic energy, but it's also going to gain potential energy because it will go up the ramp. What is potential energy? Potential energy is energy that is stored within an object, kind of waiting to be used, or waiting to show itself to the world. And there are many types of potential energy. There's only one type of kinetic energy. It's called kinetic energy. There is chemical potential energy. If you look at a stick of dynamite, TNT, which stands for the chemical name trinitrotoluene, there's chemical potential energy. A Snickers bar has chemical potential energy. If you take chemistry, you will learn, if you haven't already, that there's energy stored in the bonds of, say, molecules. And when those bonds are broken and rearranged, you can get that energy released. That's what's happening when you burn ethanol, and you get all of that energy being released. You're getting chemical energy from the chemical bonds. A 2-ton safe suspended 10 feet above Wile E. Coyote has potential energy. It's gravitational. A coiled spring or an elastic has potential energy. It happens to be called elastic potential energy. Radioactive uranium has nuclear potential energy. Electrons in a battery have electrical potential energy. There are boatloads of different types of potential energy. But a stick of dynamite just sitting on the table here doesn't appear to have energy. It's kind of hidden inside somehow. It needs a trigger. You've got to light a fuse, add a little bit of energy to trigger the reaction, and boom, it goes. If I look at a Snickers bar sitting on a table, it really doesn't appear to have any energy. But I know that when I eat it, I ingest the chemicals and my body breaks down the bonds in what I've eaten, releasing energy and allowing me to do work. I hope it's clear that that safe, if released, will do work. Coiled spring or an elastic. If I take an elastic band and I wrap up a little piece of tin foil and I put the elastic band between my thumb and finger and I take the tin foil and put it over, we've all done this, right? No? It really hurts. Don't do it because it can take somebody's eye out. And you let it go, that piece of tin foil that has been stored with elastic potential energy has the ability to do work. I shouldn't have said that. I'm going to give you guys ideas now. Obviously, a battery has the ability to do work, and radioactive uranium does as well. These are all forms of potential energy. They don't appear to have the ability to do work, but given the right circumstances, they will. Yep.
If there's an object that's just floating in space and it's not in any gravitational field, is that potential energy?
Assuming we're talking gravitational potential energy, assuming the object is far enough away that the force of attraction between it and the Earth is negligible, which means it's nothing, then no, it doesn't have gravitational potential energy. If it's a stick of dynamite floating in deep space, it has chemical potential energy still, but it doesn't have gravitational. The answer to your question ultimately is this, that when I release the safe 10 feet above the surface of the Earth, it will be under the influence of gravity and it will speed up, by the way, converting itself to kinetic energy, having the ability to do work. If that object is, quote, floating in deep space and you let it go, if it starts moving towards a planet, then it does have gravitational potential energy. Very, very tiny amount. And as it gets closer and closer, the amount of gravitational potential energy it has, paradoxically, will be greater. Even though it's closer, the force on it would be more. It's a tricky thing. So, only one type of kinetic energy, lots of types of potential energy. There is also these two types of energy. Thermal energy, which we are going to study. We're going to be doing calculations with thermal energy. Thermal energy is heat. Okay? That's what thermal energy is. And what thermal energy is a special type of kinetic energy. I think we've all been in a situation where we're cold and we rub our hands together and our hands warm up. By the way, that's a net loss of energy for your body. You're stealing energy from your whole body to warm up your hands. So it's not a really good survival technique if you're stuck in the wilderness in the cold. When you rub your hands together, it's hard to imagine, and we talk in detail about this in Physics 30, the molecules in each of your hands have electrons in them, and the electrons are found on the outside of atoms, and they're spinning around in orbits around the atoms. And electrons are negative. When I rub my hands together, the negative electrons in one hand and the negative electrons in the other hand are springing back and forth on each other. They're repelled from each other, and I'm pushing them together, and as they pass each other, they spring away from each other because they're repelled. And that causes all of the atoms and molecules to move faster. That's what heat is. Heat is all of the molecules moving faster. But they're moving faster in a random way. So, can I add energy to a baseball by throwing it? Yes. And I will be giving every molecule in the baseball kinetic energy in an organized way. So we say the baseball has kinetic energy. Can I provide the same amount of energy to a baseball by putting it in an oven? Yes. I can transfer energy to all of the molecules in the baseball, and they will all be moving faster but in a random direction, and I will have given kinetic energy to all of the molecules. But because it's random, it's heat. When I take a ball and I throw the ball and it bounces and it eventually peters out to a stop, where did the energy that was in the ball go? Because I threw it, it had kinetic energy. It's above the ground, it has potential. You know where it went? Every time it hit the ground, it left a little patch of heat on the ground. And it left a little patch on the ball that was hot. And all the molecules are moving faster. So every time that happens, the energy is being transferred to heat. So when an object is hotter, the individual particles moving faster, giving each particle more kinetic energy. But again, it's not in an organized way. You get my point here. The last point is that if I heat something up and you look at it, you can't see the molecules moving faster. But it's warmer. And how do you know it's warmer? Because when you touch it, those molecules that are moving faster bump into the molecules in your hands, causing them to move faster. And your brain has been wired through evolution to detect that as heat. It's an amazing process, actually, when you think about it. And then there's light energy. And I don't know what to tell you about light energy other than you study it in detail in Physics 30. How many of you have heard of photons? A photon is a little chunk of light. Not a proton, a photon. And it's what I would describe as energy in the purest form. There's no object with light energy. It's just a whole bunch of pure energy moving through space. It's just energy. All right, let's deal with gravitational potential energy. So what my goal here today is to remind you about the formulas with types of energy and to solve a few problems with you. So there's some kind of ride here. It's the typical ride where you have a bunch of people sitting in a car or cart or whatever you want to call it, and that cart is raised to a height. In this case, it's raised to a height of 48 meters. The total mass of the passengers in the car they're in is 500 kilograms. What's their change in gravitational potential energy when they're lifted through a height of 48 meters? Okay. So we're going to solve this problem. We're going to solve this problem in a way that we wouldn't solve it in a few minutes. Okay? But pretend you don't know what gravitational potential energy is. And I just say to you, does the cart with the people in it have energy at the top that it didn't have at the bottom? And you can say yes. And if I said why, you'd say, well, because work was done. Do you agree that work is needed to cause this cart to move to the top? And there's something I wanted to add here, but it was too late, at a constant speed. Okay? So there's no acceleration, which means there's no kinetic energy. So what we're doing is we're saying, well, since to accomplish this, you have to apply a force to the cart, and it moves through a distance, the work, which is the change in energy, is force times displacement. And now what we are at is the same kind of problem we did yesterday. I believe yesterday it had to do with a piano and Wile E. Coyote. And I said to you, we need to know this applied force. Because in the formula, work equals FD, F is the applied force. And I said, how can we find the applied force? And this was something that we thought about for a good minute or two. How are we going to determine the applied force in this example? Ephraim? In magnitude. Yep. Why? Right. Because it's moving at a constant speed, which I really ought to have put in the question, the forces vertically are balanced, which means that instead of calculating the applied force somehow, which we can't, we calculate the force due to gravity, which is mg. So we customize our work formula and get work equals m times g times d. Well, I would like you to take a minute and calculate what we get. Now, I'm not going to write down the numbers. The mass is in the question. You know what G is. It's 9.81. And then D is 48 meters.
You could have just started with MGH, right?
That's where we're going, Sam, is I'm demonstrating to you why that formula EP equals MGH is true. And I'm going to do the same kind of thing with kinetic energy. Absolutely, you could have just done MGH. But let's imagine that nobody ever taught you the formula for gravitational potential energy. That's what I'm trying to show you now, is why it is what it is. Because I think in Science 10, you're just told, here it is. I don't think anybody in Science 10 explains to you where that formula comes from. So it's 48 times 500 times 9.81. M times G times H. We're getting 235,440 joules, rather. I don't care about significant figures here. By the way, you see, I don't know if you noticed, I said Newton, no, joules. Newtons and joules are very easy to confuse. Newton is a unit of force, joules are a unit of energy. So this is the amount of work needed, and since the work goes into gravitational potential energy, this is the gravitational potential energy change from the bottom to the top, which is really then telling you that's the gravitational potential energy at the top. Okay. Use the results from the previous example to develop a general formula. Well, this formula is only valid when the work done is converted to solely gravitational potential energy. This approach in this question only works if the thing is moving at a constant speed. So we're only focusing on gravitational potential energy. Well, it's going to be the applied force times the displacement, but the applied force is the force of gravity. And since gravitational potential energy is all about lifting objects, we can call that displacement h. We already know from the previous unit that Fg is mg, and let's call the displacement h. So if this is the work done, mgh, and it's going only or solely into gravitational potential energy, we have just created a formula for gravitational potential energy. This is a formula we can use now all the time. We don't have to use the force times displacement thing. And the usefulness of this is best demonstrated by that question yesterday where I think Wile E. Coyote pushed a 10-kilogram box of nails up the ramp. And I know I talked about this yesterday, but I want to bring it up again just to show it to you. We have time. We're not in a big rush today. Was this problem? Just let everything we did soak in here. The question was, you take that box of nails and you push it to the top of the ramp, and there's no friction, and you're moving it at a constant speed. How much work is done? That's the question. But work is change in energy. And if there's no friction, there's going to be no heat, by the way. And it's moving at a constant speed, so there's no kinetic energy. All of the work done will go into potential energy. We didn't need to do any of this. And I know I did this in class with you. We could have, but I'm just reminding you, we could have just done that. You have to work smarter, not harder. And in this case, if I just said MGH, I take the mass of 10 times 9.81 times the height of 4. I didn't even have to find anything with trigonometry. It becomes so much easier. Sometimes it will be easier to use force times displacement. It's going to get more complicated. All right. So on your formula sheet under momentum and energy, you'll see that this is where the formula is. EP equals mgh. You'll also see there's another EP below it, and that's a different type of potential energy. The type of energy that I've highlighted, the type of potential energy that I've highlighted, is gravitational. The one I have not is elastic or spring. And we'll get to that later on. All right. So number 3, we have a toy car on the top of a track on a tabletop, and the question says, what is the gravitational potential energy relative to the floor? Later on, maybe Tuesday or Wednesday of next week, we'll talk about why you can measure potential energy relative to any position you want. I have in detail, just briefly though, does it make sense to say that this 3-hole punch has gravitational potential energy? Yes, because it's above the floor. Does it have gravitational potential energy right now? Well, I would argue that it doesn't, because the whole point of having gravitational potential energy is if I release it, it's going to do something. When it's sitting on the tabletop, it's really at its lowest point, isn't it? So I am allowed to say, relative to the tabletop, it has no potential energy. Relative to the floor, it does have potential energy. And when we solve problems dealing with conservation of energy, sometimes it's useful to use the floor, sometimes it's useful to use the tabletop. So what is the gravitational potential energy relative to the floor? Well, it's EP equals mgh. Anybody else up for about 0.53 joules? So about 0.53 joules. Here maybe just one final comment. That's the gravitational potential energy relative to the floor, which means if I release it, it can do that much work to something on the floor. If I would have used this height, we would have gotten a smaller number, and that would have been the amount of potential energy it has relative to that tabletop, which would be the amount of work it could do to an object on the tabletop. So it depends on the context of what it is you're after. B, what is the change in potential energy when it arrives at the bottom of the hill? In other words, from here to here, how much potential energy does it lose? Well, see if you follow this. You could, I suppose, calculate the potential energy it would have at the tabletop relative to the floor and take it away from the total potential energy, or you could just say this. The change in potential energy from the top of the ramp to the bottom of the ramp is mg times the change in its height. In other words, we can use this distance. It goes from 2.15 meters above the ground to 0.95. I don't think that diagram is drawn very well to scale. Can you subtract those two numbers for me and confirm that you get 1.25 meters? Yes? No? 1.2. Okay. So this answer would be the 0.25 times the 9.81 times 1.2 meters. It's going to be a smaller amount. And all we're doing all we're doing, I don't know what that was, is we're just finding out how much potential energy it has at the top of the ramp compared to the bottom. .29? So about 0.29 joules. I don't know, do we even need to write anything down here? MGH, go ahead and calculate it. Not quite sure why I'm adding that example. It should be obvious what you would do here, right? So about 17.640 thousand joules, or 1.76 times 10 to the 4 joules. Are we okay with number 4? I think so. So when you do work to lift an object, you're giving it gravitational potential energy. When you do work to compress a spring or to stretch a spring, you're giving it potential energy. It's elastic potential energy is what it's called. But when you do work to change the speed of an object, you're giving it kinetic energy. And we talked about this at the beginning. In order for you to give an object more speed, you have to accelerate it. So in order to accelerate it, you need a net force. And this is the formula. And only because of a conversation that came out of yesterday's class, I would like to demonstrate to you where this comes from. Okay? If you have a net force and you use work equals F net times the displacement. We did a problem like this yesterday. And it boiled down to the fact that you have to understand if the net force is times the displacement to give the work, then the net force is the applied force. Right? Work is applied force times displacement. So what if the applied force is a net force? What that means is all of the work you're doing is going into acceleration. You're not overcoming gravity. There's no lifting of the object. And that means that this must be the change in kinetic energy. And you know what? Let's even make it simpler. And I will show you guys later how we deal with it if it's a change. Let's say the object starts from rest. If the object starts from rest, then the work done will be the kinetic energy given to the object. Well, this is MA. And this is how I was taught, and I still remember it. I know that MAD will be kinetic energy, always. Always, it will be the change in kinetic energy. Because when you're mad, you throw things. Somebody, a prof or a high school instructor taught me that one time. That when you're mad, you throw things, you give them kinetic energy. So I associate MAD with kinetic energy. The acceleration can be found by using this formula. Now, I think you'll recognize, we did this yesterday, didn't we? But now I'm formally kind of just having a conversation with all of you instead of just one or two. This is because VI is 0. I'm making it simple. And I will show you what if VI is not 0 later, if you're interested. And that means that the acceleration is VF squared, which is V squared over 2D. And this is times D. Well, the D's cancel, and you're left with 1/2 mv squared. This is why this is the formula for kinetic energy. You're not expected to know how to derive that, but there's a reason for it. It isn't just somebody said, let's define kinetic energy this way. All right, let's put this into practice with a few problems. Again, on your formula sheet, here's the gravitational potential energy, and here's kinetic energy. And there are other things here. We've talked about this And we'll talk about the two equations below it in this unit. The two above it are physics 30 ideas. Determine the kinetic energy of a 5-gram bullet traveling at 740 meters per second. Well, that would be 1/2 times the mass of the bullet in kilograms times the speed squared. A very common error is to just forget to square the speed. The 5 grams converted to kilograms, you divide by 1,000. So it's giving me about 1,369 joules. First question for you is, are you getting the same answer? Okay. Let's put a context to that. Let's say that we had a 10 kilogram mass on the ground, and we want to lift it to some point. And we had that much energy, 1,369 joules of energy available. I'm not saying we're going to fire the bullet into the block and expect it to rise. Okay, that's not what I'm talking about. I'm saying if you had this much energy and you applied it to moving this 10 kilogram object up, how high could you move it at a constant speed? Well, what I'm telling you is, what if we took that 1,369 joules and set it equal to mgh? What height would we have? I would have to take 1,369 and divide by the mass and divide by 9.81, and you get a height of about 14 meters. That's a fairly big amount of energy, considering it's only a tiny bullet. Put it another way, if I move this up to 14 meters and then let it go, the amount of work it will do on your hand when it hits your hand on the floor will be 1,369 joules of work. It's a lot of energy. I mean, you do not want to put your hand under a 10 kilogram block, which is about 22 pounds, that's falling from 14 meters, right? It's a lot of energy. That's why bullets do a lot of damage. A 1,500 kilogram van has 300 kilojoules of energy. How fast is it moving? Well, we can put that 300,000 joules here, the 1,500 kilograms here, and solve for V. I know that you can take 1/2 times 1,500, but I just the way I do this, I always take the 300,000 times 2 divided by the mass, and then I take the square root. V is 20 meters per second when you take the square root. Yes? Okay, good. By what factors does the kinetic energy of an object change if its speed is tripled? Let me just ask you. This is saying if you have an object moving with a particular speed, it has kinetic energy. What if it's moving 3 times as fast? Let me just ask the question. How many of you know the answer to this is it will have 9 times as much kinetic energy? Because it's v squared, right? It's this relationship between kinetic energy and the speed. It's that. So if I triple the speed, what I'm doing is I'm tripling the right-hand side of this equation twice. If I multiply this by 3 and this by 3, and the equation must be true, this must be multiplied by 9. The answer is it will be 9 times as great. You can feel free to make up a mass, make up a speed, calculate the kinetic energy, and then triple the speed and calculate the kinetic energy to convince yourself of that fact. Sometimes I get typing and I don't really pay attention to what I'm typing. And if my keys are not quite on the home row where I think they are, it doesn't come out right. I don't know what I was typing there, but it should say it is thrown straight up. And just let me know, this is the final example. Okay. So we get a 200-gram ball, which is a fairly hefty ball. We throw it straight up with a speed of 18 meters per second. What's the maximum height using kinematics? Well, VI is 18. The acceleration due to gravity is negative 9.81. VF is 0, and you need to find D. The formula you can use is VF squared equals VI squared plus 2AD. Pretty basic kinematics problem. And if you reflect on your past here in physics and you think back to using these formulas, it was hard. Spent days and days and days practicing these formulas. This should not be hard. This should be something that is ingrained in your brain. This will be 0 squared equals 18 squared plus 2 times negative 9.81 times D. You need to square the 18 and then move it to the other side where it becomes negative, and then divide by 2 and divide by negative 9.81, or multiply 2 by negative 9.81 first and then divide by what I believe would be negative 19.62. I don't know, probably many of you are like me. I probably wouldn't move it over and I wouldn't use a negative. Okay, but when I do move it over to the other side of the equation, it becomes this, and I divide by 2, and I divide by negative 9.81. About 16.5 meters. Okay. Well, your life is about to get a lot better. Physics-wise, using concepts of work and energy allows us to bypass kinematics a lot of the time. Using work and energy, concepts in work and energy, allows us to bypass a lot of the time kinematics, and more importantly, it allows us to bypass dynamics, vector diagrams and angles and all that stuff. And that the bottom line is work and energy is all about scalars. And kinematics is about vectors, and dynamics is about vectors. So what we can do instead is say to ourselves this, that we have this ball that is going to leave our hand with a certain speed. It's leaving our hand at 18 meters per second. Moving up. This is not a vector. It's just telling you it's moving up, and at that point in time, it has that speed. Capiche? What type of energy does the ball have right now? Kinetic, yes? So there is kinetic energy here. At some point later on, the ball is going to be up here, where its speed is 0 meters per second. Right, so this is the initial point. And there's the final position. And it's not moving at that point. So it has no kinetic energy there. Right? Where did the kinetic energy go? There's kinetic energy down here. There is kinetic energy there. There's no kinetic energy here. Do you appreciate that if I just wait long enough, it's going to come back down and it will be moving at 18 meters per second? So that kinetic energy comes back. Not all at once. Where did it go on its way to the top? It did go into potential. And it didn't happen. It didn't happen all at once, right? What's happening is as the ball is going up, this is what's happening as the ball is going up. The kinetic energy starts at some value, and every joule of kinetic energy that's lost, the potential energy is greater because it's higher up. What does that mean? It means that the kinetic energy at the bottom and the potential energy at the top are equal. If you look at what we did over here on the left, that's exactly what we did. We took v squared and divided by 2 times the acceleration. But we didn't have to think of vectors. We didn't have to make a list. Conservation of energy is what we used here, which makes our lives a lot easier. And you can convince yourself that if you take 18 squared divided by 2 times 9.81, you're going to get that 16.5 meters. And not only will you get it, I mean, I think it's pretty obvious. You get the exact value, right? Because it's the same set of numbers. The problems can become so complicated using dynamics or kinematics that if you use conservation of energy or work ideas, you get the answer very quickly. There's one more little thing I wanted to show you, but I think I'm going to pause it there, and we'll talk tomorrow about it. I just want to have a little conversation with you tomorrow about why we get joules when we use these formulas. And for most people, you'd probably go, I don't care, but in Physics 30, we need to understand where units come from. You can see what the questions are. I think I've broken this down into 2 problem sets, one dealing with gravitational potential energy and one dealing with kinetic energy. For the most part, these problems are just about you using those formulas. So get to work on those, please, and I will take attendance and be around to help you out.